end. Okay, so jumping right into it. Okay, so again, we're going to start with the challenge problems. So number one, you'll notice I actually don't have an answer in red. I think I tried to at least show the answers. I didn't word it as well as I meant to, and so I apologize. And so I don't really like it. And so if you said, it says which of the following is false, if you put D or A, I would probably consider that correct. So A says the adjusted pressure increases proportionally 2 moles of gas. And what I really was trying to reference here, and again, only you guys will know if I did an okay job of this or not, but what I was trying to reference was our van der Waal equation, right? Our adjusted pressure is equal to our measured pressure P plus A, which is just some constant or some number they would give you, times n squared divided by v squared. Okay, and it was kind of alluding to that. And what I wanted you guys to kind of recognize is that as the number of moles doubles, kind of the difference between your adjusted pressure and ideal pressure would actually increase by fourfold, right? Because it's n squared in the ideal gas law. I'm sorry, in the van der Waal equation, right? And so that's what I was alluding to. If you didn't really get that, I apologize. The wording of it really wasn't that great. So I'll kind of take that on me. But again, both A or D would be kind of fine for this. Hopefully you knew both B and C, though, were true, right? So in our real gas law, also known as the van der Waal equation, the number of moles of gas is not adjusted, right? We don't have any special change to number of moles. It just appears as N, just like it does in the ideal gas law. So B would be true here. Okay, and then C says NB in the van der Waal equation represents the volume of space the gas molecules occupy, right? So remember, in the ideal gas law, we assume that no gases occupy space, right? But in the van der Waal equation, our real gas law equation, our adjusted volume is equal to V minus NB. And subtracting out that NB section is really just taking out the volume that those gas molecules do occupy, right? In N, number of moles being a part of that makes sense, because the more moles of gas you have, obviously the more volume they should take up. Therefore, you're subtracting a greater number away from it, right? Less free space. So B and C, hopefully at least you knew were true. Again, I apologize about A. It was written pretty poorly. And so again, if you wrote A is false or all of the above are true, you're getting the concepts okay. Again, it was my fault. Okay. Number two, which of the following is true about the rate of effusion? Okay, it is dependent on the molar mass of the gas, right? That makes sense because in our Graham's law of effusion, where we solve kind of the ratio, it is dependent on the molar mass. That's actually how we calculate it. So I'd say that's true. B says it is dependent on temperature of the gas. That would also be true, right? Remember, as temperature increases, diffusion itself and kinetic energy increase, which means your rate of effusion would also increase, right? I know it's not in your equation because when we solve for effusion, it's relative rate of effusion, one molecule compared to another, but your rate of effusion would increase with temperature because you just have greater molecular movement. Okay, and then C, it is the rate of a gaseous element passing through a pinhole into an evacuation chamber, right? That's pretty much just what was given as the definition of effusion in your slides. So hopefully you recognize that. And so the best answer for this should have been D, all of the above are true. Okay. Now, three, and we'll go into this more also during our review tonight, but asked, it was more of an activity to draw a barometer and 4 manometers, 2 open-ended, 2 closed-ended, and kind of showing a height differential of 300 millimeters, okay? And then kind of calculating the pressure, just so you guys can run through basically every situation you could see and understand the steps that you should take to solve for the pressure of the gas, okay? And so me personally, I did solve for the pressure of the gases, and I used 1 ATM or 760 torr as that value. But again, as long as you kind of drew this and kind of understand the concepts, that's really all this was aimed to do. Okay, so before we go on to manometers, let's look at our barometer. Okay, there would only be one situation we could see here. And remember, barometers measure atmospheric pressure, right? So you kind of have like a cylinder around just a tube in the middle. Okay, and in the cylinder lies mercury. And as the atmospheric pressure comes down and pushes on the mercury, it pushes the mercury down, inward, and up. Okay, so up the tube. And so the height differential of that mercury just represents the atmospheric pressure, and it's typically given in millimeters or centimeters. And because we're talking about mercury, your units would be millimeters mercury, for example. Okay, so if height differential is 300 millimeters, our atmospheric pressure is just 300 millimeters mercury. Okay, now let's move on to the manometers. Okay, and we're going to first look at our closed system. Okay, so it is not exposed to the environment. Okay, here we could draw it one of two ways, right? Our height differential is 300 millimeters, but we could have mercury be higher on one side or the other. Okay, and if it's a closed manometer, what I want to show you is up here, because it's closed, is actually what we refer to as a vacuum. Okay, and whenever you have a vacuum like this, you cannot have a height differential that is lower on the closed-ended side, right? This would almost tell you that you have negative pressure in this gas chamber, which just doesn't make sense, okay? And so if you ever have a closed-ended manometer and they tell you you have a height differential, drawing it like this and calculating it like this is not possible. Okay, if it's a closed-ended manometer and you have a height differential of 300 millimeters, it has to be drawn like this, okay, with your mercury lower on your gas side, okay? And how do you calculate the pressure of your gas? The pressure of your gas here is just equal to your height differential, okay? So if you had no height differential, that would just tell you that you had no gas pressure in your manometer. And whatever the height value is again your pressure in probably millimeters mercury. They might give it as centimeters mercury, okay, in which you could just convert to millimeters mercury. Now our last situation is our open-ended manometers, okay? And so here they are. And again, the height differential here is 300 millimeters. And in this situation, the mercury is lower on the gas side. In the other one, the mercury is lower on the open side that again has atmospheric pressure pushing down on it. Okay, and if you're doing one of these problems, right, and you see a situation like this, right, it's lower on the gas side, realize that the gas in our manometer has a greater pressure than our atmospheric pressure, which is why the height of mercury is lower on that side. Okay, knowing that our gas has greater pressure than our atmospheric pressure, you can pretty easily derive that the pressure of our gas should be equal to our atmospheric pressure plus the height differential. Okay, so if our atmospheric pressure was 760 torr, the height is 300 millimeters mercury, which is just torr. Our pressure of our gas would be 1060 millimeters mercury or 1060 torr. Okay, looking at the other potential option, right? Here you'll see, again, the level of mercury is lower on the side exposed to the atmosphere. This means that the atmospheric pressure is stronger than the pressure of our gas by our height differential, right? The height differential is the difference between those pressures. So the pressure of our gas here is our atmospheric pressure minus that height differential, right? Because we just said it should be weaker than our atmospheric pressure. So when we plug these numbers in, we'd find that the pressure of our gas is approximately 460 millimeters mercury. Okay, so really kind of understanding how to calculate the pressure of the gas in each of these situations is important. It's important to know the difference between a barometer and a manometer. And also, I think this concept, knowing that this closed manometer is not possible, is also pretty important. Okay, but big distinguishing factor between these two open-ended manometers. Definitely knowing which one is which is very important. Are there any questions up to this point? And we will come back to these as well during the review. I have another diagram that might be even a little bit more helpful to see this. It's not much different, but a little bit. Okay. Number 4, a piston contains 21.47 grams of nitrogen and 30 grams of oxygen at 30 degrees Celsius. The partial pressure of oxygen is 405 torr. What is the volume of the piston? Okay. And so this is actually a pretty long problem. And so one thing I would say is whenever you get grams of gas particles, right, we don't really use grams in this chapter very often. And so whenever you get, for example, 21 grams of nitrogen and 30 grams of oxygen, your first step should probably be to convert those to moles, because we can use moles in a lot more ways, okay? And so 21.47 grams of diatomic nitrogen, we divide it by its molar mass, 28 grams per mole, and we get that we have 0.766 moles of nitrogen gas. Okay, we do the same thing for oxygen, whose molar mass for the diatomic form is 32 grams per mole, giving us 0.938 moles of oxygen. Okay, now we're given a partial pressure of oxygen. And so what I'm going to kind of do is ask you to skip this part here and look at these equations, right? This is a very important partial pressure equation. And what it says is that the partial pressure of our oxygen gas, or any gas, would be equal to the mole fraction of this gas, which in this case is oxygen, times the total pressure. Now, in the problem, they told us that the partial pressure of oxygen is 405 torr, okay? And so because we're given the partial pressure of a gas, and we have information to find moles of all gases in the system, that kind of indicates that we should use this equation and that we need to find the mole fraction of oxygen, okay? And so that's what I do. I find X, which represents mole fraction of oxygen, by taking the total number of moles of oxygen I have, 0.938, and dividing it by the total number of moles. So 0.77 is my moles of nitrogen, plus 0.938, my moles of oxygen. And what I find is that my mole fraction of oxygen is 0.55. Okay, and so in this equation, I plug in the partial pressure of oxygen that we were given, 405 torr, and I plug in my mole fraction of oxygen, 0.55, and this allowed me to find my unknown total pressure. When I find that total pressure, it comes out to 736 torr, okay? which you can then convert to atmospheres using the conversion factor. 1 atm is 760 torr, and you find that the total pressure is 0.968 atmospheres. Okay. Are there any questions up to that point? Okay, so if you're ever given a problem where you're given a partial pressure and masses of gases, the grams, the masses should tell you you should probably use this information to find a mole fraction, because then you can always use this equation down here. Partial pressure is equal to the mole fraction of a gas times the total pressure, to then find your total pressure, which allows you can do a lot more from there. Okay?
I have one question. Does it matter like when we switch torr into ATM? Like if we do it at the very beginning, is that fine? Or should we do it at that step after you pretty much calculate it?
No, you could convert the partial pressure of oxygen to atmospheres and then solve for your total pressure that way. They'd come out exactly the same. Yeah, so either way. You just need to do it before this next part that we're going to get into, which is using the ideal gas law. Okay, so I did it kind of late. If you want to do it earlier, that's fine. Just as long as you convert from torr to atmospheres before plugging into the ideal gas law is completely fine. Okay, great question though. Okay, so if you wanted to convert 405 torr to atmospheres, you could do so. And your pressure total that you get right here would be 0.968 atm. You get the same answer. Okay, so now that we have our total pressure in terms of atmospheres, 0.968 atm, we can plug in our known values to find our volume, okay? So our number of moles, we actually found above when working on our mole fraction, right? So the total moles is moles of N2, 0.766, plus moles of oxygen, 0.938, giving us a total moles of 1.704 moles. So that's what I plug in for N. R is our constant, 0.08206, and T, our temperature, we were told in the problem, was 30 degrees Celsius, which is 303 Kelvin. Okay, and what's our pressure? Our total pressure is what we solve for, 0.968 atmospheres. This gives you a volume of 43.77 liters. Okay. So that's kind of a good example of a partial pressure problem. That's a very involved one. But if you get that, that's a lot of good practice with a lot of the ideas and concepts behind partial pressures. So if you get that, you are on the right track to understanding that. Okay.
Can you solve that if you were using the moles of a particular substance? Like if you're using moles of O2, could you also solve it for that as well? Like with that, with those numbers or no?
If you plugged in the moles of O2 for N and the pressure of O2?
Yeah.
I'm unsure. You could try to plug that in and see. I would, if they ever ask you for the volume, I would always use my total pressure.
Okay. Thank you.
Yep. Somebody asked about sig figs. Honestly, I don't look at sig figs ever. I got graded on sig figs 4 years ago and I left them there. Definitely try to keep track of them. But again, this is a multiple choice exam, so sig figs aren't really an issue. And again, getting the right answer is just a little more important. That's what I tend to focus on in SI. If you ever have questions about how many sig figs, and maybe that was a question, I'm happy to go back at a later time and kind of do that out with you. But for the most part, what I'm focused on is making sure the concepts are clicking, we understand how to apply the material. That's the first step. Sig figs is kind of like it's like the last 2% of the problem, kind of. It's there, and we prefer to have correct sig figs, but as long as we get the concept side, that's the big focus. Okay, so number 5, I try to kind of combine a before and after change problem with a stoichiometry problem. So it's kind of a bizarre one, but you guys have the ability to do it. So we're told that we have a container that's 2.1 liters with nitrogen gas, and it's allowed to leave or at a certain point, but when it leaves, it reacts with oxygen to make dinitrogen dioxide. Okay, you're told the pressure of the nitrogen gas when there's 0.303 moles is 3.99 atmospheres, and that when the pressure is decreased, they want to know basically how this affects your moles and then apply it to stoichiometry. Okay, and you're told that your temperature and volume stay the same. Okay, so the first thing I did here is I wrote my balanced equation, right? So diatomic nitrogen reacts with diatomic oxygen to produce dinitrogen dioxide. It's a 1:1 to 1 ratio, which is really nice. Okay, from here, I tried to just write my variables so I could get them all straight in my head. And the pressure went from 3.99 atmospheres down to 1.89 atmospheres. Our volume maintained consistent at 2.1 liters, and N, our number of moles, would be equal to 0.303. Okay, and that's going to change, and we're trying to calculate that change here. Okay, now we're told the volume doesn't change, and temperature we're given absolutely no information about. And it turns out in this problem, you actually don't need information about it. But, and so I just left that blank. And so again, this is a change problem where one condition, in this case, our pressure is the value is changing, and we are asked how a different variable, in this case, number of moles, how that changes in response. Okay, and so whenever we do a problem like this, we use this general format. P1V1 over N1T1 equals P2V2 over N2T2. And it's important to simplify this expression, right? So if a variable does not change from V1 to V2, T1 to T2, examples like that, you cross them out, right? Because they're the same on both sides. It doesn't matter their value. It's just kind of complicates your expression. And so here again, our volume and temperature don't change, so I cross them out. And this simplifies our expression to P1 over N1 equals P2 over N2. Now our P1 is 3.99 atmospheres. Our N1 is 0.303. Our P2 is 1.89 atmospheres, right? This is all given, and we can cross multiply and solve for N2, okay? And when we solve for N2, it is 0.144 moles of nitrogen gas, okay? Now the question kind of tries to tell you that the pressure and mole change occurs, and then this nitrogen is released. How I wanted you guys to interpret that is that N2, the number of moles, is how many moles of nitrogen will actually react with oxygen to produce our product, dinitrogen dioxide. And if that wasn't clear, again, I apologize. I was just trying to create a problem that was a little different. Okay, and so if we find out we have 0.144 moles of nitrogen gas, we can use the balanced equation to know that 1 mole of nitrogen gas is 1 mole of dinitrogen dioxide. Then we use the molar mass of dinitrogen dioxide to find out that we would have been able to produce 8.64 grams of product. Okay. Okay. Are there any questions on any of these challenge problems or any questions at all? Just a minute.
So for gas laws, how do you know you're solving a stoichiometry question?
Excuse me, can you just repeat the question?
Like for gas laws, right? How do you know that this question is a stoichiometry question?
A stoichiometry question?
Yeah.
So I knew this was a stoichiometry question because they refer to nitrogen gas originally, right? They tell us our volume of nitrogen gas is 2.1 liters. Our pressure is 0.30, or sorry, our pressure's 3.99, our moles of nitrogen, right? They're giving all of this information just about nitrogen gas, okay? And then if we come to the second question, the prompt, it says when this nitrogen is allowed to controllably escape, right, which means it is released, it will react with oxygen to create dinitrogen dioxide, right? So we're given all this information about our reactant nitrogen, and we're told that it's going to react with oxygen to make dinitrogen dioxide. So that sentence allows you to write a balanced chemical equation. And then the last sentence says, how many grams of dinitrogen dioxide are produced? Okay, and so whenever you're facing a problem where they're giving you, especially in gas laws, where you're given all this information, your volume, your pressure, temperature, all those things about one gas, and then you're asked at the end about a different gas. So in this case, they give us information about nitrogen, then they ask about dinitrogen dioxide. Because they're switching compounds, you know it has to be a stoichiometry problem.
Okay, I get it. A last question, Tim. How do you know if it's a gas collection or a water question?
So the key that professors have pointed out is they will typically say gas is collected by displacement of water. If you ever see the term displacement of water, or gas collected by displacement of water, that should definitely tell you that it is a gas over water question.
Okay. Thank you so much.
Yeah, no problem. Also, another thing just for everybody is notice in your gas over water questions, you're typically given, or you might be asked for, your vapor pressure of water at a specific temperature, right? And we haven't seen another problem where they supply that information, okay? And so even if you're not sure if it's a gas over water question, if they say the vapor pressure of water at 35 degrees Celsius is this, that can kind of help you understand that that's a gas over water question, because that information hasn't ever been provided in a different question, really. You know, it would either be a partial pressure question or a gas over water. And it more likely than not is a gas over water question. But the big key phrase is they will say displacement of water.
Okay, thank you.
Yeah, no problem at all. Okay, any other questions?
I have a question about the partial pressure equation. So why did you use like P equals X times P rather than P is equal to like N1 RT over V?
I'm sorry, can you repeat that? I'm trying to like draw it in my head almost to visualize.
Yeah. So for question number 4, why did you use the equation P is equal to X times P rather than like P1 is equal to N1 times R times T over V?
That's a good question. You could, I'm trying to think. You probably could also do it that way. The thing about partial pressures that I like about them, some people like about them or not, is you have 3 equations for them that are very much interrelated. You know, there's really no correct way to approach a partial pressure problem, because you can typically start it in multiple different ways and come up with the same solution. And so off the top of my head, basically using the ideal gas law to find information, that would probably work. But I don't know, this equation is just super easy to use. Also, later on, when I use the ideal gas law down here, I wanted to plug in my total moles and my total pressure. Okay, so I needed to get total pressure somehow, which I believe the equation you said does not give me total pressure. That would give me, I'm trying to think of what you would even solve for there. If you did basically PV equals nRT, you have the pressure of oxygen already. I believe you're given the, so you would basically find the volume of oxygen, if that makes sense. I would say for this problem, that one might work better. If anybody wants to stay at the end and see if it works, solving it just through one gas, I'm happy to do that. I hadn't thought of it in that way before. But yeah, if they ever ask about volume, I would say solve volume at the end through total pressure. And I use this equation because it allows me to find total pressure just very easily.
Okay, and then you said there was like 3 ways to find partial pressure. So what would be the third equation you would use?
I said about, there's only 3 equations in general. And so the 3 equations are just this one right here, that your partial pressure is equal to your mole fraction times total pressure. Your other equation would be that your total pressure is equal to the sum of all your partial pressures. And the third one is basically your ideal gas law. It's just, you know, moles of a specific gas and pressure of a specific gas.
Okay, thank you so much.
Yeah. And somebody in the chat said that they basically just plugged the moles of oxygen and the partial pressure of oxygen into the ideal gas law. And when they solved for volume, it came out to the exact same. Okay. And so if you plugged in 0.938 moles for N, and for P, you put in, you converted 405 torr, which is the partial pressure of oxygen, and you convert that to ATM. If you plug that in for pressure, apparently the answer comes out the same. Okay.
So I had a quick question for number 5.
Yep.
You know how it says nitrogen gas, and then in the second question, the second part, it says nitrogen. Does that make a difference, or they were still talking about nitrogen gas?
It was still the gas. I just used them pretty interchangeably.
Okay.
Yeah.
All right. Thank you.
Yep. Yeah, again, the actual verbal, the way I actually write the problems is probably not as good as your professor's. Again, I just try to throw some things that are a little different out there. This one's worded a little weirdly. The first one was worded kind of weirdly, so I apologize. The ones that I'm giving you tonight, I tried to make sure were pretty more straightforward. Ones that were theoretical, I tried to make sure like really made sense. I mean, I try to do that for all of them, but any remaining questions? Again, we're going to go through chapters 4 and 5, kind of each topic quickly. And if there are any questions on specific topics, I'm definitely happy to answer them then as well. Okay, but if we have no questions, because I don't want to cut anybody off, if you guys can just use this time now to sign in the chat using your net ID. Again, I kind of want to just do it at a time that there's no questions, because if somebody puts a question in the chat, I don't want to lose the question among the sign-ins. Okay, so listed here are the main 5 topics from chapter 4. Are there other things in chapter 4? Maybe a little bit, but this is pretty much the big topics. So molarity, dilution, and then your 3 types of equations, which will be predominantly what you'll be asked about on the exam. Okay. So what is molarity and dilution? And a lot of this, again, it's not typically, most of it I didn't write in a new way, so I'm sure you've seen it presented before, but molarity is moles of solute, which is typically the solid that you add, divided by liters of solution. Okay, and so we often use this to interconvert between volume and moles. Okay, and so in dimensional analysis, you'll often see you'll kind of start with a volume, you'll convert your volume to liters, and then you'll multiply it by the molarity to get moles, and then having moles of a reactant or product, you can then interconvert, right? We pretty much always use moles to interconvert. Remember, we denote it with a big M, okay? So molar, so you might see like 0.2 molar solution of something. And yeah, dilution. So remember, dilution is the process of adding water to a solution to make it less concentrated, right? Which means you decrease the molarity of the solution. Okay, and so a great theoretical question that I love is, remember that if you're doing a dilution, you can never have a more concentrated solution at the end, right? Your M1, which is your molarity at the beginning, will always be higher than your M2, Okay, so if they try to ask you a theoretical question and they mention that M2, your end concentration is higher than M1, that is not a dilution, and it's kind of possible, but not really, right? So your M2 should always be lower than M1, and your V2, your volume, should always be higher than V1, right? Because you're adding water, you're adding volume to your solution to make its concentration go down. Okay. 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 And again, if there's any questions at any point, feel free to stop me. Okay, so precipitation reactions, again, the solubility table's in the top corner. If you have any questions on how to read it, please stay after and talk to me. That is a very important topic, being able to read a solubility table. Okay, and so in a precipitation reaction, we're always going to have a solid precipitate form on the product side, right? If we don't have that, it's not a precipitation reaction. Okay, and so on our reactant side, we will typically see two aqueous ionic compounds, right? It'll be an ionic compound that is in the aqueous state. And a lot of times we'll see two, but sometimes we will see three different ones added. We typically don't see more than that. Okay, on our product side, we will see a solid precipitate, and we'll see typically one aqueous salt, but if we have three ionic compounds on the reactant side, we will have two aqueous salts on the product side. Okay, salt is just anything made out of a cation and an anion. Okay, so me saying ionic compounds up here and salt here, these are the same thing. Okay. Salts are just a cation with an anion, and they should both be in the aqueous state. The only thing that won't be in our aqueous state is our solid precipitate, which we'll see on our product side. And right, we typically see precipitation reactions as double replacement reactions, okay? Which means if a cation and anion are paired on the reactant side, they won't be paired on the product side, right? You almost just switch your anions to write the product side. Okay. Remember about our net ionic equations. Okay, so this is an equation that only includes the portions that participate in the reaction. Okay, so for a precipitation reaction, we're going to form a solid precipitate, which means the net ionic should on our reactant side include the ions that make the solid, and on the product side, it should just be our solid, okay? If any element appears in the aqueous state on both sides of your equation for a precipitation reaction, it is what we refer to as a spectator ion. That means it does not participate in the reaction, and it means that it should not appear in your net ionic equation, okay? And again, at the bottom, it's just a little note that the gray, what's grayed in, or if you're using a colored version, it would be in green. It means that it would be insoluble, which again, for precipitation reactions, we only care about what's insoluble. Okay.
I have one question for the precipitation reactions. So like, I get it when you just kind of switch the anions and all that, but like, is there ever a point where you could have like three compounds in the like reactant side? And if so, like what do you switch with what? Or is it always just going to be two for now?
Yeah, no, so that's a really good question. What I'll say is this, is that if they give you three reactants, like three different ionic compounds on the reactant side, they will most likely, if they want an equation, they will ask you for the net ionic equation. And that's actually number one on the challenge problems tonight, right? They'll typically just ask you for the net ionic. If they want a whole equation that contains all the ions, what I would do, and because you're right, it is more complicated than a double replacement, what I do is I write the solid, right? So whatever ions make the solid, I write as a solid. And then of the ions that are remaining in the aqueous state, I write them in a way so that a cation and anion are paired that were not paired on the reactant side, okay? And so that's how I do it. It doesn't really matter because they're spectator ions. We don't care about them much, which is why if you're given 3 reactants, they'll typically just ask for the net ionic. But again, if they ask for the whole equation and you're confused because it's not as simple as a double replacement, I would write whatever your solid is. And then again, for your remaining ions, just try to make pairings that weren't seen on the reactant side. Does that make sense?
Yeah, that makes sense.
Okay, perfect.
Okay, and I had a question.
Yep.
How do you know that it's a spectator ion?
How do I what? Excuse me?
How do you know that it's a spectator ion?
So for precipitation reactions, anything that does not make up the solid will be a spectator ion. Okay, so let's actually look at the solubility in the table here. Let's say that we add potassium nitrate into solution. I don't want to add potassium nitrate. That's a terrible example. I'm going to add barium nitrate into a solution, so BaNO3, and I'm also going to add potassium sulfate. Okay, so I added barium nitrate, which is soluble, and potassium sulfate, which is soluble, right? These are all going to go in. That's my reactant side. Okay, my potential products from that would be potassium with sulfate, which we know is soluble, so that won't be a precipitate. Potassium with nitrate, which is soluble and won't precipitate. Barium with nitrate, which is soluble and won't precipitate, or barium with sulfate, which is insoluble and will precipitate, okay? And so from that, we know that barium and sulfate make my product, and so these should all be included in my net ionic equation. But the potassium and the nitrate that don't form the solid product, those are spectator ions and would be left out. Does that make more sense?
Yeah, it does make sense.
Okay, perfect. Okay. If I move on too quickly again, feel free to ask me to go back or go over anything else. So acid-base reactions. Now again, we do a very quick intro to this. This is a huge topic next semester, and it's probably the topic I think students are left the most confused about, typically because we try to do just such a superficial introduction before we really dig into this topic next semester. But for this course, the titrations we focus on, and you'll see all your acid-base reactions really in forms of titration questions, they're going to be between strong acids and strong bases, right? And remember that both of these dissociate completely, okay? And so because of this, because they dissociate completely, the net ionic reaction for the titration between a strong acid, SA, and a and a strong base, SB, it'll always be H plus hydroxide goes to water. And the importance of this equation is it tells us that we have a 1-to-1 ratio, 1 H plus per 1 hydroxide. And that ratio there is something that we will see every single time in our dimensional analysis, right? I write that here. I personally do it through dimensional analysis. There is another way to solve. I've gone through it in the past if you want to see it, but I personally like this method better, okay? And so because of this net ionic equation and the 1-to-1 ratio between H plus and OH minus, we will always in our conversions see 1 mole of H per or equal to 1 mole of hydroxide. And in a titration problem, this allows us to convert from information regarding our acidic species to basic species, or it allows us to go from talking about a basic compound to talking about an acidic compound, okay? So again, you will always see a conversion that's 1 mole of H plus to 1 mole hydroxide, okay? And the keywords you typically see for this type of reaction is titrate, neutralize, react completely, endpoint. These are all just telling you that you're dealing with some sort of titration, which means that stoichiometrically it's a 1-to-1 ratio of H and hydroxide, okay? The recommendation I give to people is always start with the component that more information is given for, right? So they typically will give you the molarity and volume for either your acid or your base. And they'll give you either your molarity or your volume for the other one, right? And so start with the portion that they give you both your volume and your molarity for. Okay, and my little example here is, let's say they give you the molarity and volume of your acid, and then let's say they give you your volume of base, okay, just your volume of base. How you would approach this problem is you'd start with your volume of acid, right, and you'd convert it to liters of acid. Okay, once you have liters of acidic solution, you can use the molarity of acid they give you, so kind of the A portion here. You can use the molarity of the solution to find moles of acid. Okay, from moles of acid, you can convert and find moles of H+. Okay, from moles of H+, you can use this ratio and say 1 mole H+ is 1 mole hydroxide. Okay, and from then moles of hydroxide, you can convert to moles of base. Okay, and if they gave you volume of base, maybe your moles of base divided by the volume of base equals your molarity. That might be what they're asking about. Okay, but remember to start, if you start with volume of acid, convert to moles of acid, then moles of H+, moles of hydroxide, moles of base, and go from there. You'll see the titrations, if you look at many, many problems, they follow pretty much the same exact format every single time. Okay, any questions up to this point before we jump over to redox? Okay, so this first slide just goes over the terminology kind of quickly for redox reactions, right? So we have oxidized. So remember that something that is oxidized is an element, okay? Oxidized and reduced refer to elements, okay? Something that is oxidized loses electrons, okay? And if it loses electrons, it's going to increase in oxidation number. Okay, so looking from reactant side to product side, if something increases or becomes more positive in oxidation number, it is going to be oxidized. Something that's reduced is, again, an element, and something that's reduced gains electrons. Okay, and if you're gaining electrons, electrons have a negative charge, that's going to cause its oxidation number to decrease, right? And that's how I remember the difference between them. Reduced means to decrease, meaning the element that's reduced is going to decrease in oxidation number, okay? And if reduced means decrease in oxidation number, that means oxidized means increase, okay? Some people use Leo, the lion says gur. Leo means loss electrons oxidized. Gur in Leo, the lion says gur means gain electrons reduced. However, you memorize it or know it is up to you. You really need to know these terms. Okay. Then remember that we have oxidizing and reducing agents. Okay. And if they ever ask about an oxidizing or reducing agent, they're not just asking for an element, they're asking for a whole reactant. Okay. And so your oxidizing agent will be your entire reactant that contains the element that is reduced. Okay, while your reducing agent is your reactant that contains the element that is oxidized. Okay, so it's almost flipped in that way. Another great thing to note, or maybe even write on your note sheet. Okay. Moving on to oxidation numbers. So kind of dealing with ions and compounds in general. So some rules. So remember monatomic ions, so ions with a single element, they'll have an oxidation number that's equal to the charge, right? So iron 3+ would have an oxidation number of +3, okay? Another rule for compounds is the sum of oxidation numbers in a neutral compound, in a neutral compound adds up to 0. Okay, so if your compound is neutral, when you add up all those oxidation numbers, it has to equal 0. Okay, a very similar rule is the next one, that if you have a charged compound, the sum of your oxidation numbers have to add up to that charge, right? So nitrate ion, NO3 minus, when you add up those oxidation numbers, it has to equal the charge, which is -1. Okay, so those are general notes about oxidation numbers in reference to entire compounds or species. But how about elements themselves? So remember, an element in their natural state will have an oxidation number of 0. Okay, so any metal without a specified charge in the solid state would have an oxidation number of 0. Diatomic oxygen as a gas is the natural state. Its oxidation number would be 0. Okay, things like that. Okay, remember that oxygen is almost always -2 when it's in compounds. Fluorine is almost always -1, and hydrogen is almost always +1. Okay, so knowing these, you can pretty much figure out the oxidation state of any unknown element. Okay, and then balancing redox reactions. One thing to note is balancing here in acid and base. Base is in red because the steps in red are only applicable when you're balancing in a basic environment. Okay, so your first step is to split your reaction into 2 half reactions, right? And you're gonna balance your half reactions separately. You're gonna do this following these 4 sets of steps, right? So your first step is to balance any non-hydrogen or oxygen atoms, okay? Once you balance those, your next step is to balance oxygen by adding water molecules to one side. Then you'll balance the hydrogen by adding hydrogen ions or protons, H+, to one side. And then lastly, you're going to balance your charge by adding electrons. And again, remember that electrons bring a negative charge, and so to add it to the correct side in order to balance the charges. Okay, once you have balanced each one of your individual half reactions, you're going to look at the number of electrons. Okay, now your electrons, when looking from one half reaction to the other, should be on opposite sides of your equation, right? It should be a reactant in one equation and a product in the other. If they are on the same side of the equation, go back. That is an indication that something went wrong, because they should always be on opposite sides, okay? But the important step, if they are on opposite sides, you want to multiply each balanced half reaction by some coefficient so that the same number of electrons are transferred in both half reactions, right? So if one half reaction transfers 2 electrons, the other one transfers 3, you want the number of electrons transferred to be equal. So you're going to multiply them each by respective coefficients so that the number of electrons is the same. So in terms of 2 and 3, you'd want to get 6 electrons on either side of your equation. Okay. After you've done that and the number of electrons in each half reaction are the same, you're going to write your overall balanced equation, right? So you're going to take your 2 half reactions and write all your reactants on one side going to all your products, right? You're just combining them. And after you combine them, you're going to cancel out components found on both sides. Okay, so most of the time, you need to cancel electrons, which should cancel completely always. And then usually you'll partially cancel out water and hydrogen, okay? Usually it's only partially canceled out. They could completely cancel out, but that's a little bit more rare than partial canceling out, okay? And at this point, that last step, you would have had successfully balanced a redox reaction in acid, okay? But what if they ask you to balance it in base? Okay, what you would notice is that your balanced equation in acid has H+ in the equation. But you can't have H+ in a redox equation if you are balanced in base. And so you get rid of those H+'s by adding an equal amount of hydroxide to each side, okay? And what happens is the H+ will react with equal amounts of hydroxide in order to form water, okay? And so your last step is typically you'll find water appears on both sides when you balance in base, and so it's to partially cancel out the water, okay? A really important thing about adding the hydroxide is if you have to add 3 hydroxides to the reactant side to neutralize H+, remember to do it to your product side, right? Because your equation was already completely balanced in terms of elements and charge. And so what you do to one side, you have to do to the other to keep them in that balance. Okay. Any remaining questions on chapter 4 material? Somebody asked how you could figure out the number of electrons transferred in a redox reaction. They most likely mean in an overall reaction. And what they're asking for is, in this step, you have to multiply each balanced half reaction by a coefficient, so you have equal number of electrons on each side. Whatever your coefficient of electrons are that allows them to cancel out is how many electrons are transferred. Okay, I know sometimes it might be tempting to write 0 or transferred because they, in your balanced equation, they should completely cancel, but they're really asking before they canceled, what was your coefficient? And please just let me know if that answered your question or not. Perfect. Okay, so if there are no questions on chapter 4, we're just going to kind of run through chapter 5, right? There's not honestly that much to go over as we've gone pretty much through everything regarding chapter 5. So barometers and manometers. Okay, so remember, barometers are just to measure atmospheric pressure. If they ever say barometer, whether they specify in a different place or not in the problem, they're asking you to solve for the atmospheric pressure, okay? Whenever you're using a manometer, you're going to be measuring the pressure of some gas that's in this little circular chamber of it, right? That is what a manometer is for. It's to find the pressure of the gas in the device. Barometers are for atmospheric pressure. So again, this is kind of showing all your situations. And so here's your barometer, right? We kind of talked about how it worked, but your atmospheric pressure, which is what it measures, is always just going to be equal to the height, okay? It's that simple and easy for a barometer, okay? In terms of a manometer, remember we have 2 different types, closed and open types. Okay, and so we're going to look at the closed types first. So remember, because this portion up here, which is closed, is a vacuum, we can never have a lower level of mercury on our closed side compared to our gas. This is not possible right here. Okay, so I just wanted to show that, and again, emphasize that that's not possible. If you ever have a height differential in a closed-ended manometer, it would look like this one, okay? It would always be lower on your gas side. And your pressure of your gas for a closed manometer, vacuum, I don't know technically what the definition of a vacuum is. I would just say that it's like 0 pressure, which creates kind of like a sucking, I don't know. Not quite sure. I would say for the exam though, knowing what it means by a vacuum isn't that important. I would just maybe recognize it because they maybe could say, what is this portion? And just knowing that it's a vacuum is probably sufficient. Yeah, they won't have you define that or anything. Anyway, so a closed-ended manometer, if you ever have a height differential, it's going to look like this one here. And just note that the pressure of your gas in the device will be equal to your height differential. Okay? And then lastly, let's look at open-ended manometers. Okay, and so we're going to look at the one in the middle first. This is kind of your base manometer for open-ended. And so in this circumstance, again, it's open, so the atmospheric pressure pushes down. And notice that the height, there's no height differential. The heights are equal. When this is the case, okay, when this is the case, your pressure of your gas and your atmospheric pressure are exactly the same, okay? Now, they're not often the same. There's often a height differential. And so when there's a height differential, we have one of 2 situations. We can have this one to the left, where it's lower, the height, on the side exposed to the atmosphere. And what that's telling us is that our atmospheric pressure is stronger than our gas's pressure, which is why the level is lower. And it's lower by h amount, the height differential amount. And so here, our pressure of our gas is calculated by the pressure of the atmosphere minus h. Now, in the other situation, we could have a height differential and have the mercury lower on the side that our gas is in. In this case, the pressure of our gas is actually stronger than our atmospheric pressure. And by how much? An amount equal to h. And so P gas is equal to P of atmosphere plus h. Yes, these recordings are always recorded and posted in the regular folder. And thank
will
you.
H always be given? Sorry, I just interrupted you, but will H always be given in the question?
Unless they're asking a theoretical question, just about them in general, the only other circumstance is they could tell you the pressure of the gas and the pressure of the atmosphere and have you solve for H, but that's a pretty atypical problem.
Got it.
Okay, and so again, thank you again, Matthew, for, he said by vacuum, it's sealed on that side of the tube, so it means the pressure is not affected by gravity and only the pressure of the gas. Yeah, exactly. It's only affected by the pressure of the gas, which is why you can't have this circumstance here, because this almost says that your vacuum has a greater pressure than your actual gas, which just makes no sense. It's not possible. The height differential would be level, or it would be this situation. It just can never be this one. The ideal gas law, I'm sure by now you completely know this law inside and out. Remember, pressures in atmosphere, volumes in liters. N stands for moles. Remember, R, your ideal gas law constant, is your 0.08206 value, and your temperature should always be in Kelvin. Okay, and then my notes here are just the theoretical points that I kind of talk about a lot. Right? The ideal gas law assumes that gas particles occupy no space, meaning that we assume that the available volume is greater than the real volume available. Really, this note in parentheses is just telling us the difference between the ideal gas law and kind of our van der Waal equation, right? The volume in our ideal gas law will be greater than the volume in the van der Waal equation. Okay, and we can quantify that by NB, which is just how the adjusted volume is in the van der Waal equation. Okay, the other point is, again, we assume that gas particles do not interact and collide with one another. Okay, so this is assuming that our pressure is lower than the real pressure or the assumed pressure, right? Because there's increased pressure from this collisions that we kind of just pretend don't exist. And so the pressure in the ideal gas law will be lower than the real pressure. Okay, I forgot to include the density derivation in this review, so I apologize, but we do go over that a couple times if you want to go back and find that. But I would definitely suggest reviewing a couple density problems and knowing how to derive density into your ideal gas law. I did forget to include that in the review tonight, and I apologize. Okay, change problems. I've also called them before and after problems. These are just problems in which some conditions change, and you're asked how a specific variable changes in response to it. Okay, and this shows the derivation of the general setup. Okay, but right here is what I call is kind of like your golden equation or your golden expression for change problems, right? You're always going to start a change problem by writing P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay, after writing this kind of golden expression, cancel out any variable that does not change. Okay, so if they tell you a variable doesn't change, or if they don't mention a variable at all, assume it doesn't change. Okay? And from there, you will have a more simplified expression, and then you just plug in, you should know all your values except for one, and then you just kind of solve for that one value that you don't know, and that would be your answer. So gas over water. So this one kind of just describes the general setup. So you'll have a test tube with some reactant in it, okay, and they'll say it's heated by a flame, heating it up, and that one of the products will almost always be oxygen gas, right? Oxygen gas will be released, and it'll kind of go through a tube into water, and then the gas will rise out of the water and exist as just, you know, gas above that water. The important part about these problems is that the oxygen gas will be contaminated with water vapor, okay? And again, the key phrase for this, you know it's a gas over water problem anytime you see collected by the displacement of water, okay? So typically say oxygen gas is collected by the displacement of water, okay? And your typical problem is you're gonna be given the total pressure, the vapor pressure of water at a certain temperature, you'll be given the temperature, and the volume. You'll be given the total volume. And oftentimes you will be asked to solve for moles of the original reactant, right? So you'll solve first for your pressure of oxygen. Then using the ideal gas law, you'll typically convert from pressure of oxygen to moles of oxygen. And then using your balanced chemical equation, you'll convert from moles of oxygen to moles of your original reactant. Okay, those are kind of your main 3 steps for your textbook definition gas over water problem. Okay, if you want any examples of this, if you were not at Monday, October 26th's session, we went through 2 problems in kind of detail, gas over water problems. So if you're confused on these problems or you just want to see some examples and you haven't seen those yet, I highly recommend just looking at them. It gives you a very typical problem, which is kind of described here. And then there's one that's a little less typical that we also go through. Okay, stoichiometry. So again, we know stoichiometry is really just any time we convert between reactants and products in a chemical equation, right? The foundation for this is moles, right? Whenever we interconvert, we do so in moles. And often you might see limiting reactant problems and questions, right? Always check to see if it's a limiting reactant problem. So whenever they give you a starting amount of multiple reactants and they're asking for how much product you can form, always check, because it's probably a limiting reactant question, whether you know based on what they say in the question or not. Okay, so just always be careful and check for that. And how do we do stoichiometry in gas laws? Well, it's pretty similar to before. Just something we see is the utilization of the ideal gas law. Okay, so you'll typically start by being given one of 2 things. You'll typically be given how many grams of a compound you have, so grams of compound A, or you'll be given the pressure, volume, and temperature of A. Okay, and given this, you can convert to moles of A. So if you're given grams, you can use the molar mass to convert to moles. If you're given pressure, volume, and temperature, which you'll often be given in this chapter because it's chapter 5, right, you can use your ideal gas law to solve for N, your moles of A. Okay, once you have moles of A, you can use your balanced chemical equation to convert to moles of a different compound in your equation. So for example, I converted to compound C here, okay, and it's a 4:2 ratio based on my equation. And then once you have moles of C, they'll sometimes ask for how many grams is that, so you use the molar mass to get grams, or they'll ask either about the volume, temperature, or pressure. They won't ask about all 3, they'll only ask about one of these. And to get from moles of C to one of these variables, you would again just use your ideal gas law. Okay, that's really all kind of the only new aspect to stoichiometry in this chapter. Okay, partial pressures. So the pressure, partial pressure is just the pressure a single gas exerts. Okay, and we use it or talk about it whenever there's multiple gases in a system. And a system just means, you know, a container or some environment, right? One really important note that, again, I'm not sure how much they talked about in lecture, but has come up in the past. It was a big thing last year that they focused on a fair amount, is that whenever they tell you a volume percentage, that's analogous to mole fraction, right? And so if a container is 30% oxygen gas by volume, that means your mole fraction for oxygen is 0.30. Okay, that's a really important thing that could appear on the exam. And I just want you guys to be familiar with that in case it does. Okay, and we have three general equations we associate with partial pressures. Our first one says that our total pressure of our system is equal to the summation of all of our partial pressures, right? So the total pressure might be equal to the pressure of oxygen plus the pressure of hydrogen plus the pressure of nitrogen, so on and so forth. It just depends on how many gases there are. Okay, but when you add up all your partial pressures, that's going to give you your total pressure. Okay, your second equation is that your pressure of some gas, we'll call it gas A, is equal to the mole fraction of gas A times your total pressure. Okay, and so just remember your mole fraction is moles of some compound divided by total moles. Okay, and I probably should have written moles of A divided by total moles, because we're talking about gas A. Your last one is just your ideal gas law equation, okay? But you can use this using total pressure and total moles, okay? Or you can plug in the pressure of an individual gas and the moles of an individual gas. Now, somebody asked in a previous SI session why I don't write A next to volume, right? Why isn't it the specific volume of a gas? But typically, when we're doing questions regarding partial pressures, right, all the gases are in the same container typically when we're doing these calculations. And so because they're in the same container, the volume for every gas is pretty much the same. And it's pretty much always just the volume of the container it resides within. Okay, and so that's why we don't denote it with a little a. It's because the volume's probably the same for every single gas, which is also true for the temperature, right? The temperature should be the same for every gas. It's only the pressure and the moles that's going to change between gas species. Okay, and I believe this is the last slide. It's just quickly going over kinetic molecular theory, effusion, and diffusion. Okay, and so they don't have you calculate too much of these. Actually, they might have you plug in a little bit here. The kinetic energy is, this equation is one they don't have you use too much, but it is important to kind of understand it, right? And so the big takeaway is that your average kinetic energy is directly proportional to T, your temperature. Okay, that's pretty much the takeaway they take from this, because they focus a little bit more on this equation here, URMS, which is your root mean square velocity, okay? And that is equal to the square root, and it's the square root of all of this. So 3RT divided by your molar mass, it's of the element. The important thing to note here is that your molar mass is in kilograms, okay? It's not in grams, it's in kilograms. And this is just so that your units can cancel and that your velocity comes out with the units meters per second. Okay, the other really important note here is that your R value is 8.31 joules per moles Kelvin. Okay, it is not your ideal gas law constant. It is not 0.08206. It is a different R constant. Okay, and again, if you're going to write one thing on your equation sheet or one thing on a scrap piece of paper that you bring to the exam, because I believe you are allowed that still, unless they specified otherwise, which I didn't see anything that they did. But again, realize that this R in our root mean squared equation is not our ideal gas law R. I cannot specify that enough. Somebody asked if R equals 0.08206 in the kinetic energy equation. And I will not lie, I'm not completely sure, but I would say with 99%, that's a little too high, 95% confidence that it is your 0.08206 in your kinetic energy equation. Okay, this R, I believe, is 0.08206. And the reason why is kind of look at these two portions. It's 1.5 times RT equals 1.5 PV over N. Okay, well, PV over N equals RT. That's still, it's a derivation of your ideal gas law. Okay, so I would say I'm not 100% sure. Okay. But I would say that it's your ideal gas law constant. Okay. Diffusion. So just remember, diffusion is your movement of gases. It's random, but it is down a gradient, right? A concentration gradient. The net movement is down the concentration gradient. And just note that your rate of diffusion is dependent on, it's dependent on your molar mass, and they're inversely related, right? So the higher the molar mass, the lower or the slower the rate of diffusion. Okay, that's really all you need to know for diffusion, besides just theoretically knowing, like theoretical questions, conceptual questions. And effusion. So this is the passage of gas through a tiny hole into an evacuation chamber, which is kind of a different compartment. So it's almost like diffusion, but it's diffusion with a purpose. It's how quick does it pass through this one spot, okay, into a different chamber. And so we use this using, I think it's Graham's law of effusion is what it's called, and realize it's a ratio. So it's the rate of effusion of gas A in relation to the rate of effusion of gas B is equal to the square root of the molar mass of B divided by the square root of molar mass of A. Another thing I'd write on my sheet for the exam, because realize up in the numerator on this side, it's rate of effusion A, but in terms of the other side of the equation, the molar mass of A is now in the denominator, right? It's that little flip-flop. So definitely note that.
Is that molar mass in kilograms too, or is that one just in grams?
I would do it in grams, but you can do either one. Because as long as you stay consistent between A and B, again, I would use grams, but they should cancel each other out, so you should get the same answer either way. They're inversely proportional. Yeah, they are inversely proportional. Also, when you solve these, it kind of makes sense, right? Because if B is bigger, right, it's going to have a higher molar mass and it should move slower. But if you plug in a bigger number here and divide it by a smaller number, you're going to get some ratio like 2 to 1, right? And the 2 would be analogous to the rate of effusion of A compared to B. Okay, so why do we use kilograms in root mean squared? Because some guy way more brilliant than us figured that out. No, the reason why is if you break down the unit of joules, right? I think joules can be broken down as the units kilograms meters squared divided by seconds squared. Okay, and so the kilograms from joules, sorry, let me get to the right slide. The kilograms from joules here will cancel out with the kilograms of molar mass. And then when you take the square root of meters squared per second squared, you get meters per second, which is your unit for velocity always. Again, I think it's something you should write down. It's not the most important, but when you calculate it, if you do need to calculate it, that's definitely something you should recognize that you have to do. Yeah, and again, it does have to do with units. You are welcome. I'm not the most familiar with joules as units, but I believe Dr. Homan definitely showed it and how they cancel out. Okay, just a couple of questions that I'm answering. Do you need to know molality? They could ask about it. They covered it. It's technically fair game. But this is my 5th year around this course. Obviously taking it the first, and now this is my 4th year teaching it. And that is a topic that has always been introduced in chapter 11. Okay, they've never introduced it in chapter 4 before. And so I would say, no, you don't really need to. but maybe just write the equation on your equation sheet just to make sure in case it does come up, but it really shouldn't. Also note that molality, the numerator compared to molarity is the same. It's moles of solute, but molality, the denominator is kilograms solvent. Okay, definitely take that into consideration. But again, they shouldn't ask about that until chapter 11, which is next semester. Even one of the professors that I was talking to that didn't do those lectures was surprised it was brought up. So I don't think it would. But again, it's in the slides, and so I can't say with 100% confidence it won't be on your exam. But I'd say it's a safe bet. Okay. So here are the challenge problems. I'm going to kind of scroll through them rather quickly. I'll probably spend about 5 to 10 seconds on each slide before moving to the next. So if you'd like to take a picture, please do so quickly. If not, this session will be uploaded very soon, and you can always go back to reference these. Okay, so again, remember, we have no more session before the exam, so I will have a bonus video released tonight where I go through all these problems. I've actually started to record it. I had just a dumb mistake that made me mess up on one of these problems that I realized while recording, and so I actually have to split it up into multiple recordings, and I'll kind of just stitch them together to make them one video, but it's almost already done. I think I only have to go through 2 or 3 more questions, and then that will also be uploaded. So they should be uploaded rather quickly tonight. Density, I have no clue. Probably the first session, so last Monday. October 12th. Wait, yeah. October 12th, I should have, no, I'm sorry, it was a week ago. The 19th, excuse me. I should have gone over density in October 19th session. And also a little bit in the 21st. So all of last week, we kind of talked about density. If you do, again, kind of deriving it and just knowing how to utilize the equation with density in it should probably be enough. But yeah, I kind of completely blanked on that, so I apologize. Okay, so yeah, but I'm just kind of quickly going through the problems. So you might notice the first one, or the first 3 were kind of precipitation related. Number 4 was kind of identify a certain type of reaction. Number 5 is a typical titration question. And 6, 7, 8, and 9 are redox questions. Okay. So those are kind of, again, your main topics from chapter 4. There are other topics, they can ask about them, but they, of course, you're welcome, everybody. Your main topics are going to be on those 3 types of reactions. There's just no other ways about it. They're just huge topics, and you can ask so many questions about each of them. Okay. Once we get into question 10 and 11, these start to get into our chapter 5 questions. Just kind of a note for everybody, especially if you don't come to SI always. There are 15 multiple choice questions tonight to help you practice, but every single session I give, I don't know, probably between 5 and 10 challenge problems. And we've been going over chapters 4 and 5 for a while now, right? We've been going over them for about the last month, right? Between both of them, the last 4 weeks or so. And so feel free to go back. Just because I gave them as a challenge problem 3 weeks ago doesn't mean that they're not a good problem to help you prepare, right? Me choosing these problems for tonight's challenge problems isn't me saying that these are better problems to do than other ones. Again, I'm just trying to give you some questions that are in the multiple choice format that generally check off some of the topics that you'll be asked about. Okay, so another gas problem. Now, kind of towards the end, some theoretical questions. Again, they do tend to like theoretical questions a bit more for chapter 5 in comparison to any other chapter this semester.
What would you say is the best way to study for theoretical questions?
Good question. I mean, there's definitely no right way to study for them. I would say if you can, maybe verbally describe equations. A lot of times they'll ask about things and like they'll almost just verbally describe an equation. And sometimes people have a hard time realizing that what they're saying is like an equation that they use all the time to solve or do some calculation. So I think kind of verbally being able to describe equations can be helpful. Definitely knowing the relationship between variables, right? So looking at the equation, saying, okay, for example, the root mean squared equation, you would have to quadruple your temperature because it's the square root of temperature. You'd have to quadruple your temperature to double your root mean squared velocity. So it's kind of just, understand, especially for chapter 5, I'll kind of talk about it more specifically, but understanding really it's going to be kinetic molecular theory and effusion, diffusion, and your van der Waal equation. Those are kind of the topics that they're going to look more theoretical questions about, because they don't really talk about calculating a lot with those questions. They don't really focus on that. It's more, do you understand what is the difference between a real gas and an ideal gas? How does the equation actually account for that? So knowing that the minus NB section for the adjusted volume, the NB is representing the space that those gas molecules actually do occupy. I know that didn't really answer it. It maybe gave you a starting place. It's honestly hard. It is really, really hard to start, especially if you struggle with these questions. It's kind of more of a mindset. And so what I'd say is try not to be satisfied with things. If you are a little confused on something, ask about it. Try to learn a little bit more, because it's when you settle and say, no, they're not going to ask about that. Or, yeah, it's an equation, like I'll just plug numbers in to get it. Those are the types of things they might ask theoretical questions about. So kind of being proactive, asking questions, trying to actually understand why that equation exists, why it's written in the way that it does. Those types of things can be really helpful.
Thank you.
Yeah, no problem. Okay, so that is all. So I'm just going to end the PowerPoint here. I'm going to stop the recording. But if anybody has any questions, wants me to go back to anything, I'm happy to do so.